In this section, we'll talk about direction fields. So for many differential equations we encounter in real-world applications, it will be impossible to find a formula for an explicit solution. So how can we visualize and or approximate solutions in this case? So this section will talk about visualization, which is direction fields. And then in the next section, we'll see how to approximate solutions using numerical methods. We will limit our discussion of direction fields to first-order differential equations of the form dy dx equals f of x comma y. Now note that this equation defines a slope at each point in the xy plane where f is defined. That is, dy dx, remember, that is the derivative of our solution y, and the derivative equals the slope of the tangent line. So in other words, it gives the direction that a graph of a solution to the equation must have at each point. So for x and y, we plug those into f. That gives us the value of the derivative, and that in turn gives us the slope of the tangent line to the solution of that differential equation. So a plot of short line segments with the given slope drawn at various points in the xy plane showing the slope of the solution curve there is called a direction field for the differential equation. So let's look at a very simple example. Consider the differential equation dy dx equals x squared minus y. So in this case, this function is our f of x comma y, and that is equal to x squared minus y. So now in the point 0, 0, we have f of 0, 0 equals 0 squared minus 0, and that equals 0. So that means the slope of the solution is 0. Now at the point 1, 0, we have that f of 1, 0 equals 1 squared minus 0. That equals 1. So now our slope equals 1 in that point. And then f of 0, 1 equals 0 squared minus 1. That equals negative 1. And then finally, f of 2, 1, that's 2 squared minus 1 equals 3. Now let's represent each of these slopes by a short line segment having the given slope. So we start out in 0, 0, and the slope of the solution is 0 there. So we're going to draw a short line with slope 0 at the point 0, 0. So at that point, the slope of our solution is 0. And then at the point 1, 0, let's say that this is 1 and comma 0, or let's actually do the following. Let's call this the origin. Let's call this 1 and 2. Let's call this 1 and 2. 2 so that it's less cluttered. So at 1 comma 0, that's this point right here, we see that the slope is 1. So if we want to draw a line with slope 1, this is approximately slope 1. We can put that right there. And then at 0 comma 1 right here, the slope is negative 1. So I want to draw a line here. This is approximately a slope of negative 1. So now we have 0 comma 1. And then 2 comma 1, that's the point over here. The slope is 3. And so a slope of 3 is a rise of 3 and a run of 1. So approximately that. And let's scale that down a little bit. So I'm going to scale that down a little bit. Same direction. And so now that's a little marker that represents the slope. Slope 0, slope 1, slope negative 1, and slope 3. Now the idea is that we're going to do this for many other points. And if you have to do that by hand, that's not really doable in this manner. So we'll find one way to do this a little bit quicker with so-called isoclines. But typically this is done on a computer where you can plot hundreds of these points in one picture. So if you have a lot of these points with a lot of these markers, we will be able to get a feeling for the flow of solutions, and this allows us to sketch approximations of some particular solutions. So solutions with a given initial condition.